Okay, I want to talk about linear dependence and linear independence in a little more systematic way, especially get towards this abstract definition, but see how it's actually the right definition. But I think we want to start with the intuitive definition. And in the last video, we talked about linear dependencies, and that was always a case of just having some vector as a linear combination of others. And so let's start with that as our intuitive definition. So let's just say a set of vectors v1 through vn is linearly dependent if and only if some vector in the set is a linear combination of some of the others. So linear combination of some of the others. Okay, so that's basically what we saw in all these examples in the last video, right? Just to throw this out there, we can define linear independent. So the set is linearly independent. And this feels almost like a cop-out of a definition, but it's kind of something that you do a lot in math. But we'll give you a better definition later. But it says linearly independent if and only if it is not linearly dependent. Seems like the dumbest thing to say, but that's kind of how we define linearly independent, is not linearly dependent. Okay. Let me just give an example. Again, I'm going to use some of the same vectors I used before, but just to make sure it fits. So, example, let's think about these vectors. So I'm just going to take the first few columns of the matrix that we've had in a lot of videos this week. So this is a vector 1, 2, 3, minus 2, minus 4, minus 6, 2, 0, 1, and 3, 2, 4. And I'll even give those different names. I mean, let's call them V1, V2, V3, and V4. And what we noticed last time, or with these examples, was that V2 is minus 2 V1. And so the second vector is minus 2 times the first. But we also noticed that the fourth vector is the first plus the third. So that is V4 is V1 plus V3. And so that immediately means that the following sets are linearly dependent. So white. So we can write down some linearly dependent sets immediately. So for example, just the set of vectors V1 and V2. That's dependent because the second is negative 2 times the first. So there is one vector, namely V2, is a linear combination of V1. It's minus 2 times V1. Also, V1, V3, and V4 by the second equation. Since V4 is V1 plus V3, that immediately means that this is a linearly dependent set. So yeah, these are from the relations above. But also, I want to mention that any set containing these vectors is a linearly dependent set. So, but also any set containing either of these as a subset. for example, we could just take v1, v2, and v3. Because again, the definition is some vector is a linear combination of some of the others. And so here, v2 is a combination of v1, even though v3 is like not involved. So that's still a linearly dependent set. And you could also just say like all 4 vectors form a linearly dependent set. If I could write 2, v3, v4. Okay, so those are linearly dependent sets. Linearly independent examples. Well, v1 and v3, I claim are linearly independent. Because, well, we'll see with 2 vectors, as long as one's not a multiple of the other, they're independent of each other. They basically point in different directions in space, right? So v1 and v3, and along the same lines, actually, if you look at this equation right here, any 2 of the 3 will be linearly independent because you need all 3 to make the dependence relation. And there's no other relationship among them. So we could also say v1 and v4, or v3 and v4. We could also replace either of these v1s with v2 because v1 and v2 are so closely related. So I'll just put etc. there. Okay. So that's some examples of linearly dependent, linearly independent sets. There'll be a future video that has some more examples also, but I just want to get that out there. So, but there is a problem. So why is the intuitive definition not good enough? Let's think about this for a second. I guess what I would say is it's kind of vaguely stated, right? It's like if some vector is in the set is a linear combination of some of the other vectors. So the first thing I would say, it's kind of vague. It's also a bit hard to check, directly, sort of how do you sort of check this? Especially independence. I mean, I mentioned for 2 vectors, it's not that hard to check, but if you have like 5 vectors and you wanted to check, there was like no possible way to write one of them in combination with the others. It's like not obvious at this point how to do that. So it's hard to check, especially independence is hard to check. Okay, but so there is a sort of, well, okay, the first thing I would say is maybe let's think about potential salvages, potential definitions that might be a little less vague. So let me give you one that's like not going to work first, but it's just kind of the natural next step to think. So could we say that v1 through vn, that this set of vectors is linearly dependent if and only if vn, the last vector, is a linear combination of the first n minus 1. So if I want to, this will immediately be a little more mathematical and less vague if I write this, right? So if only if vn is x1 v1 plus x2 v2 plus dot 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 plus xn minus 1 vn minus 1 for some choice of scalars x1 through xn minus 1. So these are real numbers. So could we say that? Could we say that's our, could we use this definition? And my answer is no. Like it's not, you can't necessarily say that the last vector is linear combination of the first of the others. because we even have an example just above this set right here. Let me go back up here. So this set v1, v2, v3. v3 here is actually not a linear combination of v1 and v2. It's actually independent of them, right? These were directly related, but this is kind of a different vector. v1 and v2 point, well, in opposite directions, but they kind of make a line, and this is a different vector that points in a different direction. So in that case, v3 is not a linear combination of v1 and v2. So I'll just say, yeah, the example v1, v2, v3 above doesn't fit this, even though it's linear. It's a linearly dependent set. Sometimes I'll just drop the word linearly, especially if I'm lazy. So even though it's a dependent set. Okay. So sort of, you know, preferencing the last vector is not actually a good definition. And so we're back to the vague problem. So let's not preference any of the vectors at all. So here's a better idea, I claim. Let's go to the next page. The better idea, I claim, is, and we sort of saw this at the end of the last video. I sort of actually started doing this, and we saw how it's connected to some other nice things. Move everything to the same side of the equation. So we're not preferencing a vector by sort of saying one vector is an inner combination of the others. Going to the same side of the equation. So just as an, what am I saying here? What do I even mean when I say that? So for example, when we had v2 was negative 2v1, let's just rewrite that by adding the 2v1 to the left side and say, let's have 2v1 plus v2 equals the 0 vector. And when we say v4 is v1 plus v3, let's actually just write v1 plus v3 minus v4 equals 0. So we always end up with the 0 vector on the right-hand side of these. So why is this a better idea? I'm going to give you a few different reasons over the next few minutes of the discussion, but let me just say the reason one, maybe I should just say why better. Reason one is a purely just, I'm giving an aesthetic argument that it's a symmetry thing, that it's like, I don't really want to preference one vector of the others. So symmetry. We're not preferencing we're not preferencing or isolating one of the vectors from the others. This might not be the most compelling reason yet. I'm hoping to give you more compelling reasons, but the others. But this immediately gives you a better definition if we sort of want to write all our equations like these. Right? This actually gives us a better way to write things down. So I'm going to say a better, though abstract, definition of linear dependence is going to be the following. The set v1 through vn is linearly dependent. Again, we're going to define dependent first. If and only if we could find scalars x1 through xn, real numbers. And here's the really important thing. They're not, I'll yell at you, I'll put this in all caps. They're not all 0, such that x1 v1 plus x2 v2 plus and so on xn vn equals 0. Okay, so notice this is really the same definition. I mean, we can recover the intuitive definition, say this x2 was not 0. Then we could isolate v2 and solve it for it in terms of the others, right? And that would give v2 as linear combination of the others. So that does get back to the intuitive definition, but we've moved everything over to one side of the equation. And so that, I'm claiming this is equivalent. But here's the thing. Remember that we define linear independence as being just not linearly dependent. And that was very vague in the sense of just saying, like, that means I can never write any of these vectors as a linear combination of the others. How do you check that? So the reason, too, why this is a better way to look at things is that we can actually negate this definition and get something slightly more interesting. So the negation, I mean, there's a whole logical way to negate statements, but the negation of this gives a sort of more interesting definition of linearly independent. Gives a better definition, a better, more mathematical definition than just saying, it's not this, and it's not something. Is a better definition of linear independence. So what definition is that? Let me write that down. Again, I could just say it's linearly independent. The set's linearly independent if it's not linearly dependent, but I want to think about this. This statement right here says it's linearly dependent if we can find some constants, some scalars, x1 through xn, not all 0, so that this is true. But notice, this is true if all of these are 0, right? And so there is sort of a trivial version of this. So what we're going to do is we're going to say the set, to give the formal definition, the set v1 through vn is linearly independent if and only if, well, I'll say it two different ways. I'll say it sort of a little less mathematical first, and then I'll say it a little more mathematical. So if and if the only way that x1 v1 plus x2 v2 plus ... plus xn vn equals 0 is if all x1, x2, and so on are all equal to 0 themselves. So basically, the only linear combination of the v's that gives you the 0 vector is the trivial linear combination. So yeah, I can even say that. It's worth putting in here, actually, sort of. This is the trivial linear combination, which is 0. We're just using zeros as our scalars. Again, a slightly more mathematical way to say the same thing is with a logical implication. So or sort of written with logic, we would say basically the set's linearly independent if this equation implies implies that x1 equals x2 equals, I'm not really saying anything new, I'm just saying you'll see this definition a lot in books and stuff. This sort of, this part right here, for linear independence. Okay, you'll see that a lot. Right, and so that is a way to sort of check if a set is linearly independent. But you still might balk at this and say, well, that's not really something that's easy to check. It's just the same problem of showing that nothing's a linear combination of the rest. And that brings me to reason 3, is that some of this should start to look familiar with some of the stuff we were writing in the previous video. So reason 3, we can connect these definitions to matrices and row reduction and stuff like that. Connect these definitions to matrices and row reduction, and that will actually give us an effective way to actually compute something and tell whether a set of vectors is linearly independent or not, which is the real goal here, to give us some nice way to tell. So how do we do that? So what we do is, we have this equation, and we've seen this a few times before, right? If we have x1 v1 plus x2 v2 plus dot 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 plus xn vn equals 0, we can rewrite that as the matrix whose columns are the v's times the vector whose entries are the x's, and that equals the 0 vector. But if we call this this matrix right here A, and call this vector the vector x, then we basically have ax equals 0 is what we have, and that's the homogeneous system, right? That's the thing we've been talking about, it's homogeneous. And now we can reinterpret what linearly dependent and independent are saying. We can actually, if we think about it in terms of the solutions to ax equals 0, right? If you go back up here to linear independence and you say, and you look at this, well, if we convert this to this language right here, so in other words, then the set v1 through vn is linearly independent if and only if ax equals 0 has only the trivial solution x equals 0. It's only the trivial solution. Remember, these homogeneous systems are always consistent, right? Because you can always just plug in zeros for x's everywhere. But that's kind of what this that's kind of what this statement is saying, right? Like, we converted this first part to ax equals 0, and then this second part is just saying, well, that means x equals 0, in fact. And so that's the only solution, is the trivial solution. So this immediately gives us something interesting. We can actually take a bunch of vectors, put them in a matrix, row reduce and solve, and see if there are any non-trivial solutions. So just similarly, we can say, and, let's try that again, and the set is dependent if and only if ax equals 0 has non-trivial solutions. And really, just to put a button on this, this really gets us really far, because I'll just say, but we know something more here. We know ax equals 0 just from examples we've done we know this has non-trivial solutions precisely when A has a free variable column, right? Because, you know, if it has non-trivial solution and it has infinitely many solutions, and the only way to get infinitely many solutions is with a free variable column. And again, these can never be inconsistent. So you either have one solution, which is just a zero vector, or infinitely many solutions. And infinitely many solutions implies free variable column. So AX equals 0 has non-trivial solutions. If and only if A has a free variable column. So when you row reduce A, you do not get a pivot in every column. Right, and so that's kind of exciting. That basically gives us a characterization of linear independence. And this is the last thing I'll say in this video. But this is a way to really effectively be able to tell if you have a set of vectors. Because again, those definitions are kind of a little abstract. So characterization of linear independence. Why did I just draw that? Let me draw that later. I want to draw a big thing around the hole. Okay, so here's a characterization of linear independence. If I want to negate this statement, AX equals 0 has only trivial solutions if and only if A does not have a free variable column. So that's if and only if A has pivot in every column. So I'll even just put it in terms of the matrix. So the columns of a matrix A are linearly independent if and only if, when you row reduce, every column is a pivot column. Every column is a pivot column. And so, like with every concept we studied so far, it always comes down to pivots. And so this is a nice characterization. And so when you're asked, is this set of vectors linearly independent or dependent, all you got to do is make a matrix, row reduce, look at how many pivots there are, and that'll tell you the answer. If there's a pivot in every column, yes, it's a linearly independent set. If there's not a pivot in every column, no, there's some linear dependence. And you can find it by go solving AX equals 0 and actually finding the solutions, and they would tell you the dependencies. They give you those the scalars that you would scale the vectors by to get the dependence relation. Okay, so what I'll do in the next video is I'll actually talk a little bit about some special cases where you can always tell certain things are linearly independent or dependent. But this has been a nice, hopefully nice abstract, but gives you something effective that you can do to determine whether a set of vectors is independent or not. Okay, I'll stop.